us. A quick announcement. You have checked the final exam date. It is on Friday. I remember it. And make sure you have enough time. If you have any special requests, it's time to submit a request to the testing center right now. Don't wait, as they're jamming up with a lot of available seats they have. And also, haven't left the homework yet. I'm going to do it today because I'm trying to collect all these topics we covered in the past few weeks at quite a quick pace. So we need to get the facts in line, get all the contents there. So it takes me a little bit of time, but most of the lecture notes up to date. And one video that from last Thursday was still missing. I need to edit a little bit, but most of the videos have been uploaded to the YouTube. So you should be able to see them and review them. And now to add more questions to the database for you guys to review for the coming exam, I will do an office hour Tuesday, which is tomorrow, 3 to 4 o'clock. And if that time doesn't work for you, I can also try evening time, 6 to 7 o'clock. Just send me an email if you have any conflict. So let me say this again, 3 to 4 or 6 to 7. I'll collect the email by end of today and announce it tomorrow morning what exactly time frame that we're looking at. So during tomorrow's review session, I mainly going to drag out all the past exam problems related to the one-way slab, some of the shear, perhaps some of the deflection in terms of a cracking moment of inertia, things like that, to talk about it. And just to help you prepare, I will see if my time allows before the classes end, or maybe at the end of Thursday when we have the double lecture, I will try to add more review materials to it as well. All right. And of course, if you have any questions and need individual attention, you want to talk to me or anything like that, just send me email. We can arrange it. Okay. All right. So that's about that. And I don't think we'll have any more quizzes. So it's mainly just going to be homeworks. I think there'll be 2 homeworks. I'll leave one homework today and another homework Thursday. They will both be due on the exam date, but the last homework will not be graded. Okay, the last homework one column will not be graded. Only the homework on the past materials will be graded. That will be the homework I leave today. And also, if you have more urgent questions, say before the exam, you want to review anything like that, you can reach me through email and we can schedule time to do online one-to-one sessions, even next week when we don't have classes. Okay, so just let me know your schedule and I can work with you next week since I don't have any classes to teach next week. So timelines are pretty flexible. So if you have any burning issues, say you don't want to meet with me too much time, just want to have a quick question and shoot me an email and I can probably answer the question through the email. Okay. All right. Well, if that's it, you guys don't have any questions, let's proceed. Okay. So today,
Dr. Wu, I have a question.
Go ahead.
What is the expectation for us when we take this final? And what I mean by that is, like, since we're getting the homework questions and we have less than 2 weeks to begin solving problems for content that we've had for, we've been learning for a while. There's a number of us that are kind of wondering, like, well, since we're only going to get our first time to practice these problems, how well are we expected to do on the exam?
Yeah, that's a very good question, Drew. So 2 things I would say. One is that from previous semesters, we always cover the column in the last lecture. So the amount of time you guys have prepared for the final exam and the time you guys wait for the exam to be graded the same as previous semester. So the only thing that is slightly different is the last homework is a little more compiled homework. But again, I think we'll add one more review session tomorrow to clarify that. You'll see that most of the problems are now so intensified. So like I say, in the final exam, the shear problem and the column problem are the 2 main problems that you need to concern yourself with. And for the column problem, you will see from tomorrow to Wednesday's lecture and Thursday lecture will be very in detail. So I think if you're talking about expectations, I don't know if you want me to lower the expectations. I feel like from the first exam, this class is doing very well, and I don't see any differences in terms of understanding for a few last lectures materials compared to the previous semester. And also, you got to keep in mind from previous semester, we don't have a whole lot of homeworks approaching the end of lectures as well. There's one-way slab homework from the previous semester, I think, which is kind of overdid it. And the response I got from previous semester is that particular homework is too long and it's not closely related to exam. So I was planning to cancel it. So if you cancel that homework, in reality, we're not missing anything. You see that the homework I'm leaving today, which is going to be mainly combined of the one-way slab for some of the deflection problems. So that's things we will see, you will be able to see in the exams. I don't know, Julie, if that answers your question, but I think in short, I am not going to lower the standard. Yet, like I said again, the final exam will not be so hard as you anticipated because we're doing a combination. Instead of the whole class in squeezing one exam, we'll do a segmented exams. I think the level of difficulty will only be lower than if we do a whole exam with a lot of problems there. Does that make any sense to you, Drew?
Yes, thank you.
Yeah, no problem. Like I said again, I would not worry about the final exam as long as you understand the content that was lectured. And again, we have 2 weeks to prepare for it. Like I said, Tuesday, I'm running office hour. Make sure you're there. And I said 2 option time, 3 to 4, 6 to 7. Let me know which time works best for you. I'll have one review session with one time, but I will let you know tomorrow morning first thing. And I'm planning to add one more review session next week. But I know that you guys will be very busy. So I think I'll keep it open. If you guys have individual questions or when you study together as a group, you have any questions, we can do that. If a lot of you still have a lot of confusions, we can hold a few even review sessions next week if the time allows. All right. But like I said, again, I really don't want you guys to be stressed out about the final exam. Now, I think I'll have an updated syllabus here. I have it in my Word file. I'll update it today. But like I said, last lecture, the exam weight percentage-wise, midterm now is weighed as important as the final exam. So I think we're having a more percentage in the midterm now, right? So the last exam, which is kind of less weighted, I think should give you more confidence in getting a better grade. And I really feel like we should be okay because now the number of homeworks also reduces and you should get a very good grades on the homework as well. The homework percentage stay the same, okay? So that's to all of you. Any questions on the grading and the possibilities of the difficult levels of exam, anything like that? Now is the perfect time.
Question.
Yeah, go ahead.
But it's more about the timing of the final. You said Friday was when we have.
Oh, sorry. I think I meant to that. It's supposed to be on the exam registrar. There's an exam calendar for S&T.
Right.
Was it Thursday or Friday? I can't remember.
I think Thursday.
Thursday, right? You were right, Natalie. If that confuses you, all of you, I think I'll send the email to remind you exact time as Wednesday lecture is over. That better?
Okay, yeah, that works. Thanks.
Yeah, and also for the timing, while Natalie's added, we have about 2 hours, but I am not planning to have 6 or 5 problems. I would tend to shrink it down to 4 problems. So that way you have more time to work on the problems. And let me say this clearly, tomorrow, Tuesday, I will show you a past exam format, the type of problem you will be seeing in the final exam. And I do not plan to deviate much from the previous semesters. And I think the more important thing for you guys is to just participate, understand the type of problem and tie that to the lecture content. And then you should be okay. All right. Any questions about the final? I think you all worry about it. I like Drew's idea of summarizing the concerns you have, but I'd rather hear more directly from you guys so I have a better sense of the final while I'm making it. Anything? Do you guys all worried about it? A lot of concerns? Anything? Anything? All right, well, let's see how they unfolds tomorrow, Wednesday, okay? While I'm finishing up the column, hopefully, okay? So let's quickly dive into deflection. I don't have a whole lot of things left for deflection, but it's quite important you know the last steps of it, right? So deflection calculations, okay? So today we're going to dive into deflection calculations. All right, now a quick review of what we have done, right? So from previous lectures, we were focused on a continuously supported beam or fixed end, we call it, right? Fixed on the left, fixed on the right. And you know, the moment diagram looks like this, has a negative moment on the left, negative moment on the right, and a positive moment in the middle, right? And we call this applying moment. So MA, MA, and MA, right? This is the applying moment. Now, with this moment diagram, we were supposed to find one thing, right? That is only one effective moment of inertia, 1 IE, okay? And now, given that there's other IE effective, right? We will talk about it, but this is the IE effective you will be using to calculate the deflection for, okay? IE, okay? Now that equal to 0.5 I effective, 0.5 I effective mid, meaning the I effective midspan plus a 0.25 I effective left and I effective right combined. Okay, so that will be the equation for it. Now, I effective mid or 1 or 2 follows this equation. That is the cracking moment you calculate for this particular location. If it's midspan, it is positive. So let me just put a sign here. If it's a 1 or 2 end spans, that has to be negative. So that's the cracking moment. All right. And then divided by the apply moment, which is MA, mid, or 1 or 2. All right. And this whole thing together in a bracket and to the power of 3, multiplied by IGT, right? IGT is the transformed gross section. And that one has a positive sign as well if it's for mid section. So what do you mean by positive, right? Think of it, right? If it's positive, it means that the tension is on top. Right? So this is positive. And if it's negative, the tension is on the bottom, right? That's the difference. So positive for midspan and negative for 1 or 2, the two ends of it. Okay, so that is the IGT. Now plus is the bigger bracket, 1 minus bracket inside MCR cracking moment for the midspan and 1 and 2 ends again, right? Divided by MA, the applied moment at midspan or 1 or 2, the whole thing to the power of 3 again, and bracket close it and multiply by the cracking moment of inertia. Again, this one with a plus sign if it's a midspan, and with a negative sign if it's a 1 or 2. Okay, so this is more generic equation for I effective. Okay, so you have I effective, and then once you have it, you plug in here, and plug in here, and you get your IE for the entire span. And once you figure out this IE for the entire span, when you do the calculation for deflection, okay, for a continuously supported span length, and that is if I have a fixed end here, fixed end on the right hand side, and that's my beam right here. And ACI pretty much dictates that for this loading configuration, your deflection is going to read, let me draw that out, deflection and read in the middle. This is the maximum deflection delta mid, right? And now this is a new equation. You will see it for the first time. And I want you to box that up and put it on your creep sheet, right? That equal to 5 over 48 multiplied by ln squared, that is the span length. And when I say ln squared span length, that is a clear span, all right? Divided by E, which is Young's modulus for the concrete, okay? So this is modulus of elasticity or Young's modulus. Let me just say Young's modulus for concrete, okay? Nothing else for concrete, not for steel, for concrete, okay? And then this is IE, where this IE coming from, okay? Just cross it and put it here, okay? That's where the IE is coming from. Then multiply the whole equation, that is M mid. This is the bending moment at middle span. Usually it's positive, okay? Plus a 10% of combined M1 and plus M2, okay? 10% of combined M1 and M2, okay? So that is the deflection equation. And remember, this is for midspan. Okay, now with that, this concludes the deflection calculation equation. Today, we're going to talk about more about this deflection, okay? So what else, right? Now, Bob, you have the IE, have the moment inertia, you have this equation to calculate deflection. I just plug the number in, I should get deflection, right? What's so much that we need to worry about it, right? Well, there's nothing to worry about, just plug the number, right? However, in the construction practice, right, tells that the deflection has two components. Now the deflection has the instantaneous, instantaneous deflection, and also it has the long-term deflection, okay? So it is two types of deflections combined, okay? So why, right? So this instantaneous deflection usually means that once you apply the load to it, instantaneously you have a deflection, Then as time goes by, you also have a long-term deflection, okay? Now, specifically, let's dive in to see what's going on here, right? So there are delta total, now we call it delta total, is a total deflection, should equal to the instantaneous deflection. However, this instantaneous deflection usually is in terms of live load. I put I here, instantaneous deflection, live load. Okay, now there's also another part of instantaneous deflection that is caused by the dead load, and that one we call it delta ID. All right, pretty much just use the dead load and calculate deflection and call it instantaneous dead load deflection. But be careful. So you think of it, the live load induced instantaneous deflection will go away if you remove the live load. So once you put something on it, it will deflect. You put it away, it recovers, right? So nothing much to worry about. However, the dead load is always going to be there. So that's a slight difference, okay? Now, on top of that, some of the live load did not go away. Sometimes, some part of the live load do not go away. And this, they call it sustained live load. And usually we tell you how much percentage of the live load will sustain, okay? How much percentage of live load will sustain. So now you have instantaneous deflection dead load, and this is long-term actually. A little bit confusing, right? This is actually long-term. And this is sustained live load is also long-term. Okay, and this is actually short-term. Okay, short-term. All right, so if that's the case, how do we differentiate? The difference between the long-term and short-term is that short-term, you just calculate the deflection as it is and keep it inside the component of the total deflection. For the long-term, there are going to be coefficients applied in front of it. And specifically, we call it time-dependent coefficient lambda here. And this lambda is a variable of, it's a function of variable of T naught, which is the time point or beginning of the time point when the dead load is applied and to the infinite time, right, to forever. That is the coefficient. And then there's a lambda infinite as well for the sustained live load. So these two coefficients actually tell you how much of the time dependency of this long-term deflection you have, how much dependency of this long-term deflection you have with respect to the time, okay? So we call this lambda is a function of t, function of time, okay? And this is so-called the time-dependent coefficient, all right? Okay, so you see in terms of deflection calculation, you put the live load there and calculate short-term deflection and keep it as it is. And you put the dead load on top of it, calculate long-term deflection, multiply coefficient in front of it. And you also calculate the sustained live load cause deflection, multiply coefficient in front of it. And that consists your total deflection, So lambda t is a time-dependent coefficient. You can find this from ACI. 24.2.4.1, okay? And now this term lambda t is called a time dependent, right? So it is a function of, there's another one, c, another coefficient c, t as a function of t divided by 1 plus 50 rho prime, as rho prime is the compressive reinforcement ratio. Now I have seen rho before, right? Rho is the tensile reinforcement ratio, and rho prime is the compressive reinforcement ratio, and AS prime is the area of compressive reinforcement. Okay? AS prime is the area of compressive reinforcement, and this has to be compression. Okay? It's not tension, it has to be compression, okay? And now because CT is a function of time, okay? Is a function of time. because CT is a function of time, okay? And now that function of time reads like this. Actually, it's a quite nonlinear function, right? So this is XCT, with a function with respect to time, and this is T time. And usually this time in terms of months, 1 month, 2 months, 3 months, so on and so forth. So 0, 3, and 6, and 12, and actually 24, 36, and 48, all the way 60. Okay, 60. So that is the total time. And now if you look up into the ACI 24.2.4.1, you see this table. And when you see this table, you realize that this table capped at 2.0. So meaning the maximum coefficient you're going to get for C is 2.0. It has to be smaller or equal to 2.0, smaller than or equal to 2.0. So that means that if I draw the curve, at 3 months, I have a C equal to 1.0, right? So this is my first point. At 6 months, it is 1.2, okay, right here. And then 12 months, I got 1.4. 12 months, I got a 1.4. And then so on and so forth. So you draw the curve, it looks like this. And all the way plateaued at a 60 months. And after 60, let me just put this here. And after 60, it is the constant. It is constant 2.0. Okay. After 60 or at 60, it is 2.0. All right. So that is the equation, or that is the table where you can find the C number. Depends on how much time the load has been exerted on the structure. How much time the load has been exerted on the structure. Okay. So now to get this number, and actually lambda has 2 bounds, where one bound is the time when the load is applied to the structure, and the other is how long the structure can live, how long the structure will survive, right? So lambda has 2 variables. T naught is the lower bound, and infinity is the upper bound. So that equal to lambda infinity minus lambda T naught. Okay, lambda T naught. I can give an example. For example, if I'm trying to find out lambda as a coefficient that at 3 months, the load has been applied to the structure, and I want to find out in terms of a forever infinity, right? 1 will be the total deflection that you have, and this will get a lambda infinity minus lambda T at 3 months. Okay, now lambda infinity, you know that is bigger than 60 months, right? So that is lambda to the time of infinity, right? So that is 2.0 divided by 1 plus 50 multiplied rho prime, okay? Minus lambda at t equal to 3, and that is 1.0, t equal to 3 right here, because C is 1.0 divided by 1 plus 50 rho prime, right? So that gave you a number of 1.0 divided by 1 plus 50 rho prime. And say I have a rho prime equal to a 0.001 of compressive reinforcement ratio, usually given, or you can calculate it, right? And then I can plug this number in and get this one to be 1.0 divided by 1 plus 50 multiplied by 0.001, and I got this lambda to be 0.95, 95%, okay, 0.95, okay. All right, so that is the coefficient lambda for 3 months of a loading to forever, right? Forever. And I want you to put a notice here. This is for a very small amount of compressive reinforcement, about 1,000 compressive reinforcement. And if you say that I want to have a same lambda equal to 3 months, time equal to 3 months to infinity, but with this whole thing changes to be a rho compressive reinforcement ratio of 0.01, and this number actually reduces to be 1 over 1 plus 50 multiplied by 0.01 equal to a 0.667, and you can see that this drastically reduces compared to that. Okay, compared to that, it drastically reduces. So that tells you that the compressive reinforcement has a significant contribution to the deflection calculation. And to be precise, the more steel you have, right, higher compressive ratio, right, higher reinforcement ratio, compressive reinforcement ratio, the more reinforcement you put into it, the less deflection you have, okay? Less long-term deflection you have, okay? All right, so this is a very interesting point I just want to point out, okay? The more compressive reinforcement you have, the less long-term deflection you will have in the structure, in the RC beam, okay? All right, so with that, let's take a look at an example, right? Example. So now we're expert in calculating deflections. We're expert in calculating deflections. And I gave you a problem, right? The problem is pretty straightforward. I have a fixed support, I have a beam, and the moment diagram reads just like this, moment diagram reads just like this. And this moment diagram has a negative 225 kip foot and negative 225 kip foot, and has a positive bending moment of 162 kip foot, 162 kip foot. All right. And then I know that the applied loading has 1.2 dead plus 1.6 live. That's all I'm saying. Okay. I just put this equation here and I want to use it, but I'll show you how to use it. Okay. But I know this is the factor loading. Okay. So this is MU directly and not equal to 1.2 MD plus 1.6 ML. Okay. And now that the dead load, just give you a sense of how much the dead load, and this is unfactored. Okay. This is unfactored equal to 1.65 kips per foot, per linear foot. And this is live load is 3.3 kips per linear foot. Okay, kips per linear foot. And that is the dead load and live load distribution. All right. And I tell you that 20% of live load, 20% of live load, omega LL is sustained. Okay. 20% of live load is sustained. 20% live load is sustained. Okay. This we'll use it later. Okay. This was used later. Now, the two questions I'll ask you, and same as the exam. First is that what is the long-term deflection? What is the long-term deflection of midspan, okay? What is the long-term deflection of midspan, okay? And question B, what is the long-term deflection, okay, caused by the sustained live load, by sustained live load, okay, sustained live load. Okay, so these are the two questions. So how to solve this? Well, we're going to use that equation, right? So solve for this, I'm going to use delta midspan, and the delta midspan equal to 5 over 48, and then multiply ln squared, and EI, and this is IE, don't forget, inside bracket, middle span moment, MID, plus a 10% of combined M1 plus M2, combined M1, M2, okay? All right, so this is the equation we're going to use to find out the deflections. This is the equation we're going to use to find out deflections. And just to finish all the criteria for you, the span length, Ln or L equal to 25 feet. Ln or L equal to 25 feet. Okay, so this is the equation we're going to use to find the deflection, right? So step number one, I need to find instantaneous deflection, delta I. I need to find out delta I. And I know that delta I have delta I dead plus delta I live, two components, right? So the live load, okay, live load, total deflection, okay? Before I go on to find out each component, the total deflection is going to use this. I'm going to use this, right? Equal to 5 over 48 multiply 25 feet, okay, 25 feet. But let's convert everything back into inches. Why? Because I want my deflection on the left side to be inches. So 25 feet multiply a 12-inch per foot, and this to the squared divided by Young's modulus of concrete, that is 3,600 KSI. Where did you get this number, Bob? Well, use that equation. Is C equal to 573,000 square root F prime C, and let's just say F prime C equal to 4,000 PSI normal strength concrete, okay? I haven't said it in the problem. I should have done that. So F prime C equal to 4,000 PSI concrete, okay? 4,000 PSI concrete, okay? So that is the Young's modulus, and then multiply by I effective. And in this case, I am going to say that I give you the I effective, and the I effective equal to a 12395 inch to the power of 4. So, Bob, where did you get this number? This number we got from previous lecture, okay? Previously. And in the exam, I may not give you this number, but I give you some number. You can easily calculate this number, okay? So that is the whole thing in front of the bracket. Let me put the bracket here. It's too long, so I'm just gonna do the midspan moment, which is right here. The middle span have a 162 kip-foot of moment, and that one plus a 0.1 bracket inside and negative, because this is negative bending moment, okay? 225 kip-feet multiplied by 2, because I have both ends of it. The whole thing has to convert to be inches. So 12,000 pounds per kip, 12,000 pounds per kip, an inch per foot. And I got this number to be delta I equal to a total deflection of 0.29498 inch. 0.29498 inch, okay? And I know for a fact that this has two components, delta ID, which is the dead load, and delta IL, which is the live load. Although I don't know which percentage that each component would take, but this is the total deflection I'm getting, okay? But I can do the division now, since delta ID equal to the ratio of the factor dead load 1.2 divided by 1.2 dead load plus 1.6 live load, and that is 1.2, multiply, this is the percentage of the dead load contribution, right? Multiply by the total deflection delta I. So 1.2 dead is 1.2 multiplied by 1.65 plus 1.2 multiplied by 1.65 plus 1.6 multiplied by a 3.3, and this whole thing multiplied by the deflection of 0.295 inches. And you know what? I got this number to be delta ID, instantaneous deflection dead, equal to a 0.0805 inch. 0.0805 inch. Okay. Now I do the same for the live load. I do the same for the live load, and that is 1.6 live load divided by the 1.2 dead plus 1.6 live. Okay, and again, this is multiplied by the instantaneous deflection calculated previously, and that is 1.6 multiplied by 3.3 divided by 1.2 multiplied by 1.65 plus 1.6 multiplied by 3.3, and this multiplied at 0.295 inch. So I got this number to be a 0.2145 inch. All right, okay, so that, ladies and gentlemen, are the instantaneous deflection. Hence, I have no interest in find out only the instantaneous deflection. What I need to find out is long-term deflection. Remember, per the problem, long-term deflection. So I say, I don't know, but I know the total deflection to forever, to eternity, equal to a lambda coefficient of eternity multiplied by the dead load induced deflection plus a delta instantaneous deflection and live load. And this is short term, by the way, short term, just to differentiate, okay? This is short term. And plus another long term, which is lambda, to the time where the sustained live load has been applied to the structure and multiplied by the live load induced, or sustained live load induced deflection. Okay, so all I have to do is find out these coefficients, right? Find out these coefficients and also find out this fellow here, because I have this check, from previous calculation. When I don't know this fellow here, and this fellow here, right? I don't know them three, so let's just do it, right? So lambda infinity should equal to c at the time of infinity divided by 1 plus 50 rho prime. Remember the equation? And now we know that infinity is definitely longer than 60 months, right? So 2.0 on the top divided by 1 plus 50. And let's just say I have a reinforcement ratio of 0. So no compressive reinforcement. Assume no compressive reinforcement, okay? Now, when the problem didn't tell you that, you can simply assume that. Why? Because that gave you the maximum deflection, so it is more conservative. Okay? So this way you get 2.0 divided by 1.0, you have coefficient of 2.0 for lambda. All right, now you have that, then lambda to the T naught infinity, that is the beginning of the time when things start to be applied to the structure. And I assume that I have that since the beginning. So this is c to the infinity minus c to the 0 So this is 1 plus 50 multiplied rho prime. Again, rho prime equals 0. So on top of it, I have 2.0 minus 0 divided by 1 plus 50 multiplied 0. So I got a 2.0 again. Okay, 2.0 again. Easy. All right. Now I have this thing checked. This thing checked. All I have is sustained live load cause the deflection, right? Cause the deflection. So let's take a look at it. So sustained live load caused the deflection, right? So I called it LLSUS, right? Sustained. And I know that that is only 20% of the total live load. So the deflection must be 20% of the instantaneous deflection caused by the live load. So 20% of that gives me 0.2 multiplied by 0.2145 inch. And I have a final number for this one is 0.0429 inch. All right. Now you have this fellow as well. Plug in everything back into this equation, and eventually you got a total deflection delta infinity equal to a 0.4613 inch. Now to answer the problem A, it's called asking the long-term deflection, which is a total deflection equal to 0.4613 inch. And B, asking the deflection caused by the sustained live load, and that is 0.0429 inch. And voila, we're done. All right, so you see, it's not too bad, isn't it? Okay, I went by very fast because it's all about plugging in and find out the CE. CE is this curve right here where you can just plug the time in and find the numbers. And you say that, oh, hard to find all these numbers, but trust me, right? When I give you the tables, I only show you 1.0, which is 3 months. So let me just put this line here. 1.2, which is 6 months. 1.4, which is 12 months. And when you have 60 months or more, you have a 2.0. So you only need to remember 1, 2, 3, 4 points. Okay, you only need to remember these 4 points. And that's all you need to know for the deflection calculations. All right, so it's not too bad. It's not too bad. Now, as I'm going super fast, I want to show you the past year's exam, okay? I want to show you the past year exam, okay? So strap in, give me a few seconds. But while I'm pulling the files, any question about this? Any question about this? Anything before I review the final exam from previous years? Anything? Anyone? All good? Problem? Anything? Okay, well, if required, let me show you something, right? Let me show you something. And I don't want to show names. I need to show a, okay, let me show a problem that is more generic so you can see it better. Okay, 1 second here. Okay, let me do this. All right, do you guys see my PDF? Anybody? Okay.
Yeah.
Okay, good, good. So this is the past year's final exam, okay? I want to quickly show you. Now, this is the effective flange for BE monolithic. We have done this in the first part of it, so you will not see this problem, okay? Now, for 1B, problem 1A, 1C, all this, right? All these are in the first part of the exam. You will not see this, and you will not see this, all of this, okay? Now, you see the 1H is about moment coefficient, okay? So all we have done is show you the structure and ask you to find the moment coefficient, okay? Ask you to find moment coefficients. All right. And then we will try to ask you what kind of span length you need to use to find out the numbers. That is pretty straightforward. Okay. Now, this is the deflection problem. This is a deflection problem I want to share with you. So let's read together, right? So a beam with a cross section below, which is a T-beam, simply support at 20 feet. It's subject to uniformly distributed load, dead load 1.5, live load 6.62. Compressive strength concrete 5,000, yield strength of bar 60 KSI. Now, knowing that, you probably don't need the yield strength, right? You don't need the yield strength, okay? Now, here's a nice part. The following property have been determined. The following property have been determined. That means the cross section is given. The transformed cross section is given. The crack is also given, okay? That means we spent some time in the previous lecture trying to ask you to calculate 3, but in the exam, the homework, usually they're given. All right, usually they're given, okay? So I don't have to worry about the detailed calculation if I were you for the final exams, okay? And also on top of the mid-span deflection for simply supported beam, okay, be careful. This is simply supported beam, not continuously beam, okay, not continuous beam. It's given this much, okay. Note that the concrete cover at the bottom 3-inch right here. So blah, blah, blah. First thing, find the cracking moment. So how do you find cracking moment? How do you find a cracking moment? I gave you a few minutes, right? Read the problem. Now a few minutes, maybe 30 seconds. I have 5 minutes left. Read the problem, right? So I want to ask you, how do you find a cracking moment? Let me ask some folks here. Well, let me see. Drew, are you there? Drew, are you there? Drew, are you ghosting again? All right. Well, if Drew's not here, let me try next one. Who's here? Let me find another guy here, another lady as well, maybe. See who's here. Jonathan, are you there?
Yeah, I'm here.
Hey, how are you doing? Doing okay?
Good. How are you?
All right, not too bad. So quickly here, when you see this MCR as a cracking moment for this T-beam, right? First thing first, how do you calculate MCR? What pops in your head first? Well, give you some hints, right? This is a nice T-beam, right? First of all, it's a simply supported. Do you see this?
Yeah.
Right. So let me ask you this. For simply supported beam, where is the maximum bending moment at? Mid-span or support?
That'd be a mid-span.
Mid-span, right? So that's the maximum bending moment. A good one. Next question. If it's a mid-span, would you say it's a positive bending or negative bending for simply supported beam?
Positive.
Positive, right? So it's got to be positive, right? Why that is so important? Because if it's positive, we know that the tension is at the bottom or top.
It'd be in the bottom.
Bottom, there you go. So to find out the cracking moment, all you have to do is use the neutral axis, right? And find the distance between the tensile side of it, which is the bottom or top?
The bottom.
Bottom, right? So the distance between the bottom line here to your neutral axis. Since you already know the cracking moment, right? Or sorry, you already know the gross section IG and IGT, right? And you can actually calculate the MCR using the FR IGT over Y bar, YT, and the YT distance is from the neutral axis to the bottom one. So all you have to do for this one is just find the neutral axis. So how to find the neutral axis? Jonathan, how to find neutral axis for this one? Oh, you look at this T section, right? So what do we do with the T section? You divide them into two components, right? How do you divide them? You divide them into a web, which is bottom part, or the flange, which is the top part, right?
Yeah.
So how do you find neutral axis? That is to find a Y bar, right? Do you remember the equation how to find a Y bar? Y bar top equal to, it's a fraction, right? And the top, there's got to be Y1, remember? A1 plus A2.
Y2.
Y2, there you go. The bottom,
A1 plus A2.
There you go, right? So that is equation to find the neutral axis. So from there, you can actually get your cracking moment. Okay, so that takes about 5 points. Next one, determine the effective moment inertia considering a full dead and live load. Show all your work. Wow, this is too much, right? I effective. How do you do that? Full dead and live load. How do you do that? By the way, thank you, Jonathan. So let me find my next guy here, or next person here. Who's here? Let me see here. Let me see. I have my few frequent list I do for victim. Brett, you there?
Yep, how's it going?
Not too bad. How are you doing, man? Doing okay?
Yeah.
All right. Okay. So quick question for you, sir. So I effective, right? IE, right? Now, what we just talked about, I want to give you a fair hint, right? What we talked about just now in the lecture, there are two conditions. One is continuously supported, fixed end, remember? The two ends are fixed. And the other is for simply supported beam. All right?
Right.
For simply supported beam, you use that equation MCR over MA to the power of 3, right?
Right.
Yeah, for the other one, the continuous support I use like mid span 50% of that plus 25% of the ends, right? So my question to you is that which one do you use?
The first one.
The first one, right? There you go. So it's not that bad. So this one, you just need to find the M crack. So if I can annotate on this, so all you have to do for this one is MCR, use that equation MCR over MA to the power, MA to the power of 3. And thank you, by the way, Brett. And then IGT, and this is simply supported. So you only have positive bending moment of positive IGT, okay? Plus a 1 minus bracket inside MCR, MA to the power of 3 again, and bracket outside, multiply I crack. Now IGT is given from the problem, ICR is given from the problem. All you have to do is apply MCR and MA. What is MA? What is MA? MA is the bending moment of this midspan. So all you have to do is find out the bending moment of the midspan, apply the bending moment for the midspan. Okay, so that's the job, to find out the maximum bending moment in the midspan. How to find out the maximum bending moment in the midspan? It's a simply supported beam, right? So simply support it. Now I have a dead load and plus live load, so you need to find out omega U equal to 1.2 dead plus 1.6 live, right? So you have this distributed, uniformly distributed apply loading here. And the moment and the middle span for this simply supported beam, middle span for the simply supported beam is 1/8. Finally, for the first time, use that equation, okay? MU is 1/8 omega U L squared. Omega U is what you calculated here. L squared is the span length. What is span length? 20 feet, right? So L equal to 20 feet. And voila, you find out the bending moment, right? And this is MU, but it's actually in the middle span, right? So this is what we have in terms of MA, the moment diagram, okay? All right, so actually that's not too bad, right? You find out MA, you plug in that equation, MCR of MA, things like that, and you find out IE, okay? Now, once you have IE, right? Now the next question is, once all the loads are applied, what do you mean by all the loads applied? Meaning everything's applied in the get-go from very beginning of the time, okay? And I want to find instantaneous dead load deflection delta ID. How do you do that? Instantaneous, right? So I'm just going to use this equation, and instead omega here or W here, I put WD, and actually to be more precise, 1.2. So this here, W equal to 1.2 dead load, okay? 1.2 dead load. So that will go into the deflection calculation to get your instantaneous dead load. Okay, when you see this instantaneous, right, there's no lambda in front of it, so there's no time dependency, okay? No time dependency for this one, okay? All right, so that's not too hard. Then move on to the next one. Once all the live load applied, everything applied is the live load deflection. You do the same. Instead of delta ID, you have delta IL. So here, instead of delta, sorry, only 1.2 dead load, you have a 1.6 live load, and just plug in that one, and you can get this number here. Okay, you get this number here. All right, okay, so 2C and 2D seems to be trivial, right? Not too difficult. Last one. If the same beam is used as floor supported and it could be damaged by large deflection, determine the amount of deflection that will occur in 10 years, okay? In 10 years. So first thing, what is 10 years? What is the 6 months? 6 months, 16 months, 60. 60 months is 5 years. So 10 years means almost forever. 10 years means almost forever, okay? Assume the partition will install 3 months after shoring of the beam is removed. All these words, okay? All these words just tell you that the live load, delta ILL was, so delta total, this is basically delta infinite, okay? This is delta infinite, right? So that all this word tells you that lambda in front of live load start from 3 months to infinity. Why infinity? Because 10 years, that's more than 60 months. 10 years is more than 60 months. So we have a 10 year, more than 60 months, that means forever, okay? That means forever, okay? More than 5 years, that's just forever in our book, okay? Then this is delta ILL live load, okay? And there's a coefficient in front of it, plus, sorry, not live load, yeah. My bad. This is dead load, okay? This is delta I dead load, okay? Dead load, okay? Plus and live load, ILL instantaneous deflection, okay? Then plus another lambda plus another lambda, and this is called sustained. So the sustained, oops, so let me just correct this. This is now 3, okay? This is beginning, because the dead load is applied in the beginning, okay? Dead load is applied at the beginning, okay? Only the sustained live load, which is right here, and that is from 3 months, okay? And this is the sustained, live load sustained. Okay, and let me explain to you, right? It says that assume the partitions are installed 3 months after shoring the beam is removed. So meaning that the beam was shored 3 months, and after beam shoring is removed, you put the partitions. So that means the 25% of the live load is sustained right here, right? This takes place after 3 months. So the time coefficient for this one is 3 months to infinity. Now the dead load is pretty much there all along, right? The dead load is pretty much there all along. So that is from 0 to infinity. Now you have this number to be the dead load calculated previously. You have this number to be the live load calculated previously. You have this number to be 25%, so the quarter of 0.25 of this number right here. So that is how much of sustained live load you have here. Okay, and then find out the coefficient lambda infinity, that is 2.0, and lambda infinity 3 to infinity 3 is 1.0, infinity is 2.0. The difference is actually, difference is actually 1.0 divided by, don't forget, divided by 1 plus 50 rho prime, okay? 1 plus 50 rho prime, and this is 2.0 divided by 1 plus 50 rho prime. And fortunately for you, for us, that in this section, do you have any compressor reinforcement? Let's take a look. Let's take a look, right? I have a what? I have a simply supported section, the middle span, which is positive bending moment, and I only have tensile reinforcements, so rho prime equals 0, right? Rho prime equals 0. So to finish that, basically, I have a delta equal to a 1 divided by 1 plus 0 and multiplied by the live load, multiplied by the dead load plus a live load and plus a 1 divided by 1 point plus O, and this is, sorry, this is 2.0 because it's infinity, okay? This is 1.0, there you go. So this is 0.25, 25% of the live load. Okay, and I have dead load previously calculated here, I have live load previous calculated here, so this is same. I can easily plug them in and get my deflections. Okay, all right, so one more sentence, I'll be done, okay? Why am I doing this? Why am I doing this? I'm trying to show you that although the concept is fairly new, the problem is not hard, all right? The problem is not hard. So I will not panic. I will try to reason why we have deflection calculation, how we can get a deflection calculation using simple concept. Okay, all right, so I'll leave the homework today, and you're welcome to stay behind if you have any questions. And also, I'll send you a time for our office hour tomorrow, and please make sure you can attend. So we'll talk about the previous exam, and I'll upload this previous exam to the Canvas today. Okay, all right, well, that's it. Thank you so much. See you tomorrow, okay?